Mathematics in Nature and Art, the Golden Ratio and the Fibonacci Sequence. While math might not be the first thing that comes to mind in the context of art, it does show up quite a bit more than expected, and also in nature. One example of a topic for both is the Golden Ratio. First, let's explain what it is. Given a line segment divided into two unequal parts, the parts are in a golden ratio if the ratio between the larger part and the smaller part is equal to the ratio between the whole segment and the larger part. This gives the equation a over b equals a plus b over a, and when solving for the ratio of the larger to the smaller using the quadratic formula, we get 1 plus the square root of 5 all over 2, which is approximately 1.618, and is written with as a constant with the Greek letter phi. This ratio shows up in quite a few ways in geometry, mainly in shapes such as pentagons and pentagrams, shown here with highlighted edges that happen to be in the golden ratio, decagons, which are not shown here, the golden spiral here, the golden rectangle, also shown here, and Kepler's right triangle, which is shown here, and in some other places. There are a few different ways to construct the golden ratio geometrically. Here within a 1 to 2 to root 5 triangle, here around a 1 to 2 to root 5 triangle, and here through the midpoints of a equilateral triangle inscribed in a circle. Also related are the Fibonacci numbers. Beginning with the two numbers 0 and 1, the next number in the sequence is generated by adding the two previous numbers. This gives a sequence starting as 0, 1, 1, 2, 3, 5, 8, 13, 21, and so on. So for example, we can add 13 and 21 to get 34, 21 and 34 to get 55, 34 to 55 to get 89, and the series simply continues from there. Sequence. It can also be computed through a formula called Benet's formula, such that the nth Fibonacci number, with the 0 being 0, is equal to phi to the power n minus phi to the power of minus n all over the square root of 5, which does use the golden ratio. For example, plugging in the value of 12 gives an output of 144 as the 12th Fibonacci number. Now the limit of the ratios of consecutive Fibonacci numbers also approaches the golden ratio as numbers get bigger. So for example, 5 divided by 3 is about 1.6666, while 21 divided by 13 is approximately 1.615, which is slowly getting closer. The concepts of these numbers dates back quite far in Indian mathematics, for example in composing poetry of different lengths, but was first introduced to the Western world by Leonardo Pisano, aka Fibonacci, in his book Liber Abaci. The sequence first showed up in a problem about simplified rabbit breeding with pairs that reproduce a new pair every month as each take a month to mature. These rules give rise to the same generation rules as the Fibonacci sequence. Since the number of new pairs that will show up in the next generation is equal to the number of mature pairs in the current generation, which is in turn equal to the number of total pairs in the previous generation, each generation has the same number of pairs as the sum of the previous two. And that's the same generation rule as the Fibonacci sequence. Now, The Fibonacci numbers and the golden ratio are incorporated art in a few ways, though some of those examples are partially disproven or entirely disputed. Starting off, Luca Pacioli's book Divina Proporzione, illustrated by Leonardo da Vinci, directly explored the ratio's mathematical properties. Though the presence of the ratio in da Vinci's other works, such as The Vitruvian Man and the Mona Lisa, is mostly debunked, as he used a different system of ratios for the human body. Salvador Dali's painting, The Sacrament of the Last Supper, also uses the proportion explicitly, for example, using a golden rectangle as the size of the canvas, and also using a dodecahedron as the motif for the window, which is made up of pentagons and therefore has the golden ratio intrinsically. Swiss architect Le Corbusier also explicitly incorporated the ratio as part of his design philosophy alongside human measurements. Meanwhile, claims of the ratio's involvement in the design of the Giza pyramids, mainly regarding Kepler triangles, is difficult to substantiate due to multiple other possible ratios, while claims regarding the works of Piet Mondrian, the Parthenon, and the Cubist group Section d'Or either have all missing or incorrect evidence regarding related measurements and whether or not they're related to the golden ratio. Now, a similar set of cases occurs in nature. The Fibonacci numbers show up in many places in genetics, such as in the ancestry of ants and in the possible sources of human X chromosomes among their ancestors. They also show up in spirals in the distribution of plant parts called phyllotaxis, which exploit the fact that the golden ratio is irrational as an offset angle alongside other angles and related sequences. In this case, the number of spirals going clockwise inwards and going counterclockwise inwards are two consecutive Fibonacci numbers. Aperiodic tilings based on the golden ratio have been discovered in real life in the form of quasicrystals. Meanwhile, claims that the human body contains many examples of the golden ratio generally fail to account for the level of variation in human proportions. And while many logarithmic spirals, such as snail shells and galactic arms, are called golden, most are spirals of a different ratio. Anyway, in this next part, I will be showing you a few ways to compute the golden ratio and to prove that Binet's formula gives exact values for the Fibonacci numbers. Demo 1. Computing the golden ratio. Now, given that phi can be defined as a over b, where a and b are two line segments such that a plus b over a equals a over b, we can rewrite this equation as which simplifies to now substituting in the value of phi. Moving all terms to one side. And multiplying all terms by phi again. We get a quadratic equation equal to 0. Now solving it using the quadratic formula. Now, the quadratic formula would give two possible values, but given that this is a ratio of two line segments that is decidedly greater than 1, we know to take the positive value. So we find that phi is equal to 1 plus the square root of phi over 2, which is approximately equal to 1.618. Demo 2. Proving Binet's formula. Now, Binet's formula is a way to compute the nth Fibonacci number using only the index number. To prove it, we will be using mathematical induction. A few notes here regarding some identities of phi and its negative inverse, and the values of those two constants. So first, we will begin by the basis steps of showing that Binet's formula works for the two lowest values. For f sub 0, we get which is equal to which simplifies to 0, which is in fact f sub 0. Next, for f sub 1, we get which is equal to, which lastly simplifies to 1, which is in fact f of 1. Next, we move on to the inductive step. The rule about generating Fibonacci numbers is that they are the sum of the previous two. So, taking the sum of two consecutive numbers in Binet's formula, we get combining denominators, we get Next, we take out common factors from both. Next, we use the identities we saved from earlier. We combine the exponents. And we can recognize this as Binet's formula again, So that means that we can get the final result of f sub n. Thus, for every number in Binet's formula, adding the two previous gets the next one, which means that it satisfies the recursive definition for the Fibonacci numbers, and since both of the basis steps are complete, the Binet's formula must satisfy the Fibonacci sequence for all values.